In this video, I'm going to take a quick look at the simple linear regression for the BMI and fitness data using RStudio. And I'm not doing anything fancy, and all these commands are in the notes for the other example that I put in the notes. So I've basically copied all the commands across and relabeled them for this data. So when you're working in RStudio, make sure that you set your working directory to your file location and make sure that you're reading in your data file from, like if you've got a subfolder, make sure you put it in there. This case, we have a CSV file. Previously, I think I've used a lot of Excel files, but you can read in either. I'm just going to call this my BMI data. Normally, I would probably label it. I put this note down here. I could probably move it up a bit. Usually, I think I would name my data and my model after the main outcome of interest, but because it's fitness in this case, it kind of abbreviates to fit, and then it's a little bit confusing if you start looking at fitted values. So I thought I'll just call it BMI for ease of reference. So we're doing a scatter plot first. So let me go back through the plots. Actually, I didn't redo the plot to put the labels on. I personally would do the plot first without changing the labels, just to make sure you've got them in the right order. And then when you're sure it's doing the right thing, add your labels in, because it is possible that you could plot these the wrong way around and your labels don't actually match up to what you did. And that would be a problem. So when we're doing a scatter plot, it goes the X variable and then the Y variable. But then when we run the linear model, it goes the Y variable then the X. So you have to remember which way around you're doing stuff in R. So this will give us the scatter plot. And then to add the linear regression model on, it's this abline command. And it's based on the linear model of fitness by BMI. So this command here will add the line to the plot once you've already done it. So you can do the plot first and then add the line on after, and that's fine. So we've got our scatter plot up. We can see there's a bunch of problems with it. It's not really a strong relationship. It's possible there might be a curve, and that can look different on how you scale the data. But there is a lot of variation in here. So we can see that BMI is not a good predictor of fitness. And I have linked to the original paper in the notes, so that if you would like to read the original paper, you can. And if you want to see what they tried when they were trying to look at this relationship, you're welcome to look at that. This data is not the actual data they used in the paper. I don't have access to that data, so I have kind of faked this data to give similar results. So the sample sizes won't match up and you won't get exactly the same results that they get in the paper, but we're looking at a similar pattern. So we've done our scatter plot. After that, I would then go ahead and run the model. I think I have a stray comma in here. I'm not sure why. So here I have changed the way that I've referred to the variables. In this one here, I did the data $ variable, and here I've got the variable and then said what the data is at the end. So you can do it whichever way you want to do it. And I'm saving this linear model into another variable name so that I can then refer to it and get other information out of it. So I'm saving this linear model as a variable, and it hasn't told me anything. I have to ask it to actually give me a summary. So the output is not very pretty. We get here the output probably in the reverse order from how Jamovi gives it to us. So we have the estimates for the intercept and the slope, which are here. Actually, so that's the intercept and that's the slope. So if we wanted to make an equation of fitness is equal to intercept plus slope times BMI, this is where these numbers are coming from. We have a very small p-value saying that the slope is significantly different from 0. Our adjusted R² is here, and that is telling us we are explaining less than 9% of the variation in fitness with our model, which in this case is just a simple linear model. And we have the overall f-test, which is testing, is this model predicting anything better than what we would get if we just predicted the average for everyone? And the p-value is the same as for the t-test. So if you have only one variable in your model, the t and the f-test will give you the same p-value. The test statistics are different because they are actually different tests. They just end up testing the same thing because the model is so simple. But if you have more variables in the model or a more complicated model, then the f-test is testing the whole model and the t-test is testing each variable separately. So although they can end up being the same test, they're not always testing the same thing. So that's all the information we get out of here. The model is significantly predicting a proportion of the variation in fitness. For every increase of 1 on the BMI scale, we're getting a decrease in average of 0.08 of fitness on this standardized measure. So if you want to know what they did with these college students to measure their fitness, you can go and read the whole paper. They put them through a whole bunch of tests, I suppose, or fitness activities to measure it. And then they've standardized the scores. So when we standardize, we're centering it around 0. So 0 does not mean zero fitness, it means average fitness. And higher than 0 is higher than average fitness, and then less than 0 is less than average fitness. So we've got a few outliers in the lower end, which is helping kind of form this impression of a curved relationship here. After we've run the linear model, then we would want to take a look at the residuals. So we can save these residuals as another variable, which is what I'll do here. And then we can plot the fitted model against the residuals. So the fitted values are on the x-axis and the residuals on the y-axis. So we're now going x, y, whereas the linear model was y, x. I realize that's a little bit confusing. It'll probably make more sense when you've done a lot more statistics and done more linear models as to why this is kind of written the other way around. It's so that you can add more stuff into your linear model. So it doesn't have to just be BMI. We could add other variables in there too. So we want to add them in on the right-hand side. However, it's convention that when you refer to a plot, you do plot X, Y. So it's just different traditions, I guess. So we have our fitted values, and I haven't changed the labels. You could make these fancier. And we have our residuals. And because we've got a fairly simple model, these are basically showing us the same pattern that we could see in the original data. But as your models get more complicated, the residuals can look quite different. And here again, it does look like there is perhaps a bit of a curved relationship, which you can have a look at in the paper. They have a go at fitting that. Now we're interested in if the residuals are randomly scattered around 0, so we can add in a reference line at 0. I'm not sure, it looks like there's a little bit of a pattern. There might be some increase in variance, but overall it just looks like it's not a very good model. The other thing we're interested in is, are the residuals approximately normal? It is possible to do a test for normality. If you have a really big data set and there's anything a little bit going on, it's quite easy to fail that test. So I would recommend just having a look at the histogram to see what's going on with the residuals. Just a simple linear regression model, I guess, is reasonably robust as far as the limitations of the model go. So this is not a great model to start with. So the fact that it's a little bit not normal, it's probably a little bit too peaked, and maybe there's a little bit going on here in the extremes, and it's not balanced on both sides. And I think that's probably related to this slight curve. So you may be able to fix that normality by adding in a quadratic term. I'm not sure, I haven't tried. But I don't think that's really the biggest problem with this model. The biggest problem is that it's just not a strong relationship, and I think it needs a little bit of a curve in there. So that's as far as we're going with linear regression in this subject. There's more diagnostic tests that you can do. There's more ways that you can add things into a model. You can make them more complicated by adding in more variables and by adding in curved relationships. which you'll probably do in a later subject, but this is as far as we're going here. So it's important that you are able to understand the output. In an exam, I think I'm going to put in the output from Jamovi just because it looks so much better and it's so much easier to navigate. The plots look fairly similar, so it doesn't really matter which package makes them. So you should be able to understand the output from a linear regression and interpret each of these graphs. The last thing that you might want to do for a different set of data is plot the residuals in the order that the data was collected. So not overly important, I think, for this data set, but for an experiment or something where there is perhaps a time element to it, you do want to check that there is an increasing variance or something happening partway through the experiment. So in that case, probably the easiest thing to do is to add in another column here, just numbered 1 to whatever your sample size is, and just assuming that you have put the data into your sheet in the order that you collected it, you can then plot the data in the order that you collected it with that extra variable. Okay, I think that's it. Let me know if you have any questions. This script file will be up in the scripts folder on Blackboard.